Okay, so hello everyone. I would like to thank the organizers for inviting me here. It's a great pleasure to be here. It's a wonderful place. And the title of today's talk is Diagnosing Phases of Matter using Photonic Correlation Functions. So this work has been performed at the University of Maryland in the group of Mohammed Hafezi in collaboration with Gautam Nambiar, who is the leading author of this research. So conventional methods for probing strongly correlated matter include, for example, Raman, palm probe spectroscopy, and in all cases, basically the input field and the scattered photons can be considered as just classical fields. And the question I'm going to explore in my talk is basically what can we infer from the quantum statistics of scattered photons on the system when we treat it as basically several photons. And I'm going to demonstrate that correlations between scattered photons enable novel probes of mode insulators, in particular spin and mixed spin charge degrees of freedom. I will provide dictionaries between correlation functions of photons and matter. I also demonstrate that by measuring the correlation functions of these scattered photons, one can measure spin chirality and also detect signatures of fractional statistics. So let me give a brief overview of Raman scattering in strongly correlated mode insulators. Consider basically, for example, a Fermi-Hubbard model at half filling in the limit of very large Hubbard U. The low energy sector, I'm sure everyone is familiar with that, is encoding the spin states, and the upper Hubbard band is the charge degree of freedom. And now if we consider non-resonant inelastic light scattering in this system of laser frequency being sufficiently detuned from the Hubbard gap U, then this inelastic scattering process is governed by the so-called Fleury-Loudon operator, which is a purely spin operator. And the intensity spectrum of the scattered light is given by this correlation function of these Fleury-Loudon operators. This method has been, of course, explored in strongly correlated spin-liquid candidates with broad continuum of spin-on excitations emerging at very low temperatures. But generally, it's very hard to interpret the data. And the question that I'm going to explore is, what if we scatter more than just one photon on the system and measure other correlation functions, not just the normal ordered product? And in this case, so in Raman, it is known what's the relation between light and matter. So, but what happens if we scatter more photons? How do we relate light and matter degrees of freedom? Of course, when we pump more excitations to the system, this is this has been explored in the so-called palm probe spectroscopy. Here, one drives the system with one or several pulses that are sufficiently strong, which are coupled to the matter proportional to some operator B, and then one expands some observable A in terms of nonlinear response coefficients chi, which are some nested commutators of this A and B. And and then by analyzing this chi 2, 3, n, basically one can study strongly correlated systems, and it has been demonstrated that this way one can study properties of spin-on excitations in 1D transverse field Ising models, detect signatures of Majorana fermions in Kitaev honeycomb materials, and also probe fractional statistics in topologically ordered quantum spin liquids. Another manifestation of this chi-n nonlinearities in optics, it has been known that is the ability basically to generate correlations between scattered photons as measured by this correlation function of the photon field Gn, which roughly measures the endpoint correlation functions between photons. So in the limit, when, for example, chi3 is infinite, the two-level system, it is known that basically the G2 function vanishes for the same time or like 0 time delay, just due to the fact that a two-level system cannot be excited more than once. Of course, there are more exotic scenarios like this Rydberg polaritons, where these polaritons are actually attractive, leading to values of the G2 function which are greater than 1, as shown here. And this is all measured by some device that I'm going to explain in the following slides. But interestingly, it allows not only to measure just the density type correlation function of photons, but also infer the relative phase of photon propagation through the material. More recently, this kind of techniques were explored in a condensed matter setting in a group of Professor Martin Klassen demonstrating a many-body photon blockade, and also in a group of Angel Rubio demonstrating entanglement phase transition, which can be observed by monitoring the field of the cavity. So in my talk, I'm going to be interested in the strongly correlated Hubbard models. So here's the outline of my talk. First, I will define the photonic correlations that we will be interested in this talk. Then I will describe multiple photon scattering in a mode insulator, and then I'll proceed to the applications. So in my talk, I'm going to be interested in these 4 correlation functions. All of them can be measured by a so-called Hanbury-Brown twist interferometer, or it's some minor modifications. So here, the scattered signal from the material is split into 2 arms of this interferometer using beam splitter, and then they're supplemented by 2 detectors. Then the first correlation function, or it's just basically the intensity, also proportional to average photon count rate, is given by this formula where E plus and E minus are the positive and negative frequency components of the electric field. And this I is basically a projection onto the filter polarization if one is present in the detector. And in the following, I will just denote this electric field operator by some bosonic mode operator A of the corresponding detector. And I assume it's a stationary process which oscillates at some carrier frequency omega signal. Then the next order is basically the G2 correlation function, and this is 4-point correlation function of the electric field. And roughly, this can be understood as a joint photodetection rate, which measures coincidences in photon arrival, basically at the 2 detectors with potentially some additional time delay tau. Finally, the last 2 correlation functions is so-called quadrature of the light field. So it's basically A plus A dagger average and some of its fluctuations. Both of these correlation functions can be measured by mixing the scattered signal with a strong field of the local oscillator, and then by performing measurements in basically each arms of this a bit extended interferometer. And then quadrature is just can be found by subtracting the 2 intensities in, for example, one of the arms, and its fluctuations can be found by measuring the G2 in each of these detectors and subtracting across the G2 of the 2 arms of the interferometer. So now once we define this light correlation functions, the natural step is now to find what basically, how are they related to the matter correlation functions when we scatter on the Fermi-Hubbard model. But before that, I would like to point out the following property actually of the light scattering in just the quantum systems. So it's basically scattering in a most in the smallest quantum system one can imagine, the 2-level system. For example, here, if one scatters like small number of photons, then there are a limited number of diagrams that basically photon scattering can take. So here, if in a single photon subspace, the photon can only scatter elastically to the same frequency as the input laser. But for 2 photons, there are 2 options actually. So it can either scatter twice elastically, or it can scatter inelastically with the quasi-resonant excitation of the upper basically state. And then it undergoes again transition to the ground state. In this case, it generates sidebands of the spectrum. As can be seen, it's just this basically omega plus delta and omega minus delta emission. And the interesting property of this basically simple picture is that if we just measure the G2 correlation function of the signal, then obviously, as I already mentioned, we can find the, without any filtering, that it's just 0, because it cannot be excited twice. But if we filter the signal, then actually G2 can be anything pretty much. So, for example, if we filter the central peak, it can be 1, or sideband is just greater than 1. So it basically, it means that statistics of light is not just the property of the emitter, but the filtering and basically optical scheme plays like a very crucial role in the scattering process. So let me now proceed to the scattering of photons in a motor insulator. So basically we consider a standard Fermi-Hubbard model with nearest neighbor tunneling and a strong on-site repulsion U. We add the light matter coupling via the Peierls substitution. So A here is a gauge field. Then the light Hamiltonian has the standard form where lambda parameterizes both momentum and polarization modes. And for simplicity, we're going to just expand the interaction Hamiltonian in powers of the gauge field, and these terms just resemble the usual paramagnetic and diamagnetic terms, but we will, I mean, it's not necessary in principle. So in the large Hubbard U limit, the spectrum of the Hubbard model essentially splits into sectors which are parameterized by the number of Halon-Doblon pairs, with the lowest energy sector being given by this essentially spin Hamiltonian, which is the Heisenberg antiferromagnetic Hamiltonian. So now we're interested in scattering of light in the system. For that, we set up a scattering formalism. We assume that in the asymptotic path, the state of the combined system is given by some state in the spin sector and by coherent state of the light, coherent state of the light in a particular mode with momentum K laser, which is also proportional to the frequency of the laser. Now, then we are interested in what happens with the state in the asymptotic future. We just apply the scattering matrix to the state, which is given by the standard time-ordered exponential. Then we can expand this scattering matrix in terms of non-interacting states of the whole system. And here we get this appearing, the effective T-matrix formalism. So all in all this is solvable, but it's too complicated still to find the final answer. And for that, we employ several approximations. So basically, we assume that light-matter interaction is sufficiently weak. And in this case, we can define the following small parameter, which is equivalent to an effective Rabi frequency corresponding to this EA dipole. A is the lattice spacing of the Hubbard model. So it's a ratio between effective Rabi frequency to the laser frequency. So then the finite structure constant is small. And also, we assume that the light is sufficiently detuned from the upper Hubbard band. In this case, each absorption and emission of photons comes at additional price because the light-matter interaction is weak. And in addition to that, we assume we post-select photons. For example, for two-photon processes, we assume that we always measure G2 correlation functions of the field. And we also filter photons such that their frequency is sufficiently close to omega laser, with potentially some deviation of the order of the detuning from the upper Hubbard band. In this case, the final result can be written explicitly. So, yeah, an important property under all of these conditions, the stateness, basically the state after the scattering necessarily returns to the spin sector, and that allows to write the final result in a closed form. As expected, it contains amplitudes where 0, 1, or 2 photons were scattered, and it's also shown in this schematic figure. And the corresponding action on the matter in this process of scattering is parameterized as R1 and R2 operators that I'm going to discuss in the following. And also, in principle, if one is interested in additional filtering in the system, one can multiply this scattering state by an additional scattering matrix with the corresponding to Fabry-Perot resonators. So let me start with the just single excitation scattering, which is just conventional Raman scattering. As expected, it's given by the Floridel-Don operators, which are some of the spin singlet projectors convoluted with the polarizations of input and the scattered light. So here I also ignored the momentum transfer between light and matter, and I also, in the presence of polarization filter, we can just define these operators. So basically the polarization of emitted light is the same as polarization of the filter. Now, since we have explicitly the outstate of the system, we can find all correlation functions. And just as a summary, basically the effective input-output relation is that we need to replace the photonic operators with matter operators, which are Floridel-Don convoluted with the effective filter functions. And this way we get just standard Raman expression. So now the two-photon scattering is more complicated. So how much time? Okay. 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 Yeah, the two-photon scattering is now more complicated, and here I represent all the relevant diagrams, and I will go over them one by one. So the first diagram represents the configuration of scattering when system necessarily returns to the spin sector after emission of the first photon. In this case, both of the emitted photons have frequency close to the laser frequency, it can be seen, and it can be shown that the effective matter operator that controls this emission and absorption processes is just the usual Floridel-Don operator. Next, there is a configuration where after absorption of a second photon, the system ends up in a charge sector. And so there are three of such diagrams, and the last one corresponds to application of diamagnetic term within charge sector. And as can be seen in all of these diagrams, one of the photons is always emitted at the frequency of the Hubbard, of the order of Hubbard band U, and we denote the corresponding matter operator as C lambda. And another photon is always emitted as a 2 omega laser minus U, as very similarly as in two-level system case. And we denote the corresponding matter operator as B lambda. In principle, these two operators can be found analytically, but they are extremely cumbersome, so I'm not going to reproduce them here. But importantly, the asymptotic scattered state can be expressed as just time-ordered products of these operators, either A or C and B. And with the important constraint that B operator always acts first on the matter because it's just mandated by causality of the scattering. So now, assuming that the charge sector width is of the order of Hubbard T, spin sector is of the order of T squared over U, and if we detune the laser sufficiently from the upper Hubbard band, we can always filter the components of scattered field which correspond to either evolution purely within spin sector or within mixed spin charge sectors. So I will be using this fact in the following. So let me just summarize the effective input-output formalism for the two-photon scattering. So here I just take an example of G2 correlation function. So in order to relate this G2 correlation function to the matter, we just need to replace again the photonic operators with the convoluted matter operators, where M is either A, B, or C, depending on where filter is tuned. So we kind of have this control over what kind of energy sector we want to explore. Then B has to be always acting on the matter first, and we also need to impose additional time ordering, which just appears due to expansion of the scattering matrix. So as an example, if we apply this procedure to G2 correlation function, we get the following formula where A1 and A2 are the Floridel-Don operators.
So here you're doing measurements of photon counting in real time, but then you're applying these filter functions in terms of kind of energy windows. Is there some assumption you're making there in terms of what the line width is, or separation, or frequency scale, or coherence time?
Well, you mean of a filter? Or
Yeah, of the filter, because it seems like if you're doing a real-time experiment, you may only have coherence between the photons over some real-time window, so then you may not know all the frequencies in your problem because you can't Fourier transform from time equals 0 to infinity.
well, I don't know. So it kind of is the same. So the same, like temporal or frequency is kind of the same. So you either multiply in Fourier space or do convolution in real time. So there's no difference. So it's like you imagine you just scatter light and then you have an additional scatter, which is Fabry-Perot resonator. That's our model, basically. So then the width of Fabry-Perot, I mean, do you mean the width of photon because of some other processes, not just many-body decoherence? Or
Yeah, so I think my concern is just here you have these multiple photon operators at different times, whether they're actually correlated due to any decoherence mechanisms that might
no, right.
them.
We don't include any decoherence mechanism except for, I mean, there is, I mean, you always entangle actually with the matter. So you can think of it as an effective, you can see that some of these amplitudes are actually corresponding to matter being entangled with light after you scatter. And if you trace over matter, you get actually just some states will not have coherence, for example, but you can still filter them. It's just some, noise. So
Okay, yeah.
so it's more like many-body decoherence in this sense, I guess. Yeah, so let me benchmark our formalism with the simple toy model of Heisenberg antiferromagnet given by this Hamiltonian. So we can perform the usual Holstein-Primakov and Bogolyubov transformation and linearize the dispersion. So here I assume we filter within spin sector such that all operators are effectively Flory-Loudon operators. Then we can apply exactly the same Holstein-Primakov and Bogolyubov transformations to the Flory-Loudon operators, get these long expressions with alpha and alpha prime and beta being some form factors which are momentum dependent. And now we are interested in a connected correlator of this basically 4 operators. So for example, there's many processes that come into play when we plug just these operators. But it's much easier to explain with the graphics. So the first incoming photon necessarily creates like a Magnon pair with the opposite momentum. And then there are several options for the second photon. So it can either create another pair of magnons, and actually this contribution can be shown to be like effectively a disconnected contribution to the G2 function. Then there is another option that second incoming photon annihilates the first Magnon pair, and actually this contribution turns out to be dominant contribution to the G2 function, which is connected one. And finally, so both of these first contribution scale is unsquared. And finally, we have 2 more contributions which are subdominant in the number of lattice sites, where we either scatter without changing the Magnon number, or where we scatter on this, where we create exactly the same Magnon number as the first photon created. So the important feature, so all this is linear magnons, so no interactions between them. And in this case, I will not go into technical details, but by choosing filters and polarizations, so we can actually filter all of these components that I'm showing you. So there is a way to basically eliminate non-interacting Magnon bath from the G2 correlation function. And this is especially important if you want to consider some effect of interactions on the G2, for example, which I'm going to show on the following slide.
Why do you say that this is the dominant contribution?
Dominant in the number of lattice sites. So these different contributions, they have different scaling in terms of number of sites. And dominant, I mean, yeah. And it's easy to see, actually, but okay. Okay, let me now discuss more exotic kind of features of. So here, for example, if we take a Heisenberg model, in addition to just antiferromagnet, it can also have ground states which are quantum speed liquid ground states, which exhibit no long range order down to 0 temperatures. And for, depending on some microscopic parameters like lattice structure and also the interactions, the state can be topologically ordered, and its excitations can have fractional statistics. Now, recently, in these two papers, the authors proposed a way to monitor the braiding of anyons, and that requires observation of a response function of very specific temporal structure, which is written here. So I will first explain how it can be measured in a realistic experiment, and then I will briefly sketch what it means physically. So consider light scattering, and so let's assume we scatter 2 photons on the system, and first photon is sent directly to the detector, while the second photon, which is shown in green here, is sent to a scheme which allows to measure the G1 correlation function of photons. So, moreover, we record the signal only in case when the first detector clicked. So that kind of measurement is called the heralded G1 measurement, and effectively this is a post-selection on the first detection process, and it has explicitly this temporal structure with T and tau being controlled by an additional delay lines which can be present in the system. So that accomplishes the how it can be measured, but now what it means physically. So here I just follow the argument for a physical kind of interpretation. So let's assume that we filter in spin sector, then we apply our input-output formalism, we replace photonic operators with Fleury-Loudon operators, we get this similar structure. And now when we act with the A1 operator on the vacuum, this can create a pair of anyons, and then we have a second photon which is detected, and that can create another pair of anyons, which is then annihilated at T plus tau. Then this universal contribution to this H correlation function comes from those trajectories where actually the 2 anyons braid between themselves. And it can be shown that it is proportional to this area where the first anyon just should be created in order to propagate into this circle of the second anyon, times the recombination amplitude for the second basic anyon pair to recombine after all. And that provides this square root of time type behavior of the correlation function. I should note that in principle, the optical scheme that we propose for measurement of this braiding is generating exactly the temporal structure which is required, well, at least in this proposal one. And in palm probe scenarios, there would be additional commutators involved in the formula. So finally, let me discuss the measurement of static spin chirality operators. These operators acquire finite expectation value in chiral spin liquids. And before answering how to measure them, it's convenient to list all the symmetries which these operators obey. And so basically they are odd under time reversal, spin singlet under rotations, invariant under lattice rotations, and odd under reflections. So it has been known that static spin chirality operators appear in the expansion of Fleury-Loudon operators to higher orders in basically in the tunneling strength. And in this case, they would contribute to the Raman scattering as a fluctuations of the basically of spin chirality operators. Now, if we apply our input-output formalism and measure just the expectation value of the photonic operator, that implies that we can just directly see the expectation values of static spin chirality on Kagame lattices. Now, what about other lattices in addition to Kagame? So we now consider the triangular lattice and assume that we scatter light on Fermi-Hubbard model, measure in a charge sector, in this case, not in spin sector. So we measure B and C operators, and we look at the result of homodyne detection of the signal. So we find that homodyne signal is proportional to some of static spin chirality operators of this form, which I show here. And we also find that the symmetry channels of the basically polarization operators is also consistent with the required symmetry channels for the static spin chirality operators. So here, importantly, one may ask, so how is it possible that by filtering in charge sector, we can measure something within spin sector? And here, actually, the answer is that we, by looking at zero time delay between the detection events, we can post-select only those configurations where excitation doesn't spend much time in the charge sector. So even if it's excited there, it should emit immediately due to this post-selection process. So with this, I would like to conclude. So yeah, in this talk, I basically described the photonic correlations as a novel probe of quantum matter. So I derived the input-output relations, and I described several applications for spin-charge correlations, spin liquids, including fractional statistics. And of course, there is a lot of space for follow-up research, for example, the quantum input states and full counting statistics of both the input and scattered. And also maybe there are some extensions on some excitonic systems with the fractional phases. Yeah, thank you.
Thank you very much, Andrey. So we are perfectly on time.
Thank you. So I have a very naive question. You know, when you do photon correlation measurements, you look for signatures like bunching, anti-bunching. So it wasn't clear to me what you would observe in this case. So what is your prediction?
Right.
I mean, it's, let's say in the simple Fermi Hubbard
right.
model.
So it depends where you filter. It's the same as with two-level systems. So for example, if we look at the sidebands, it would be strongly bunched because there's no like lowest order photocurrent essentially. But for central, for the spin sector, I would guess it should be also bunched because there is excess noise. So the state is basically quite incoherent in some sense. So we scatter, and there are many components that remain entangled with the matter. And when we trace over the matter, because we observe only photons, these components should look like some incoherent noise over the photonic degrees of freedom. So I would assume that the spin sector should be rather also bunched.
So actually, do I need the incoming photons if I just like monitor, put photodetectors near a material and thermal or quantum fluctuations? Could I also try to collect noise statistics?
Oh, yeah, but at which frequency? Well, yeah, I mean, you mean that, so here it's optical or infrared, so I guess that would have very small, the spectral function in this region would be very small, I guess. So you mean equilibrium system, but you want to monitor it at high frequencies with available single photon detectors. So it just doesn't emit usually anything.
Something in between a comment and a question. So does it make, I also relate to the question which was asked before, because I would expect that if I am in the charge sector in a real system with dissipations, this will not be observable, in the sense that the phasing will be too fast, and I will, if I understand correctly, it would be impossible to measure in these very short times. For whatever I naively, this is something I would like you to comment about. I would have expected that it's much more realistic to observe what you said about the spin sector, because coherences could be preserved longer, in a sense.
But
to understand correctly.
Yeah, but no, that's right. But I just would like to understand. So here we essentially assume that we'd never excite charge sector. So this correlation function, for example, it's a 0 time delay, which means it's almost equivalent as if it was off-shell, actually, excitation. So it's like leaving immediately sector after excitation, because we post-select. Maybe it will be hard to do it with a realistic detector. But there's kind of many layers of why it can be possible or not. But, so in principle, I don't see why not. Yeah. So maybe detector width is insufficient because, okay, so this is 0 time delay, so this will be constrained by detector width. So that might be one option, for example.
Yeah, this correlator is still in the spin sector, as Andrey said, because the time delay is 0. The system gets no time to get excited to the charge sector. It immediately leaves. So it's not, the charge sector has no time to decohere here with charge excitation.
Yeah, the comment is more than whenever I would use a real light source. Okay, I would always mix correlators at different times. That's and in a sense, but this is a very naive comment in the sense that I would have expected that whenever I'm in the charge sector, all this coherent evolution will be lost nearly immediately.
No, indeed, if we look at finite time delay, that would mean that we create the blown hole pair, which start propagating, and many things can happen. But yeah, here it's basically as if it was off-shell. Then there is maybe a constraint on detector capabilities, which we assume these are perfect detectors.
Yeah.
So the previous talk was in the charge sector, right? So if you didn't believe the experiment from the
But maybe I can ask a question about that.
I don't. Yeah, I would have the question Eduardo didn't allow me to ask to the previous speaker was whether he plans to use like to see this effect with fields which are phase stable, mid-infrared fields which are phase stable, so that you would be able to see the full quench of this and the dependence. But in a sense, that approach, what I would say just naively as an experimentalist, is that approach would benefit a little bit of a longer coherence in the charge sector because he uses mid-infrared pulses which sustain a little bit coherence for a little bit longer. This would be the comment, but this would be a question to Matteo.
Just a quick comment. No, the mid-IR in the previous talk was already phase stable, so the experiment was already CEP stable. The reason why you don't see the subcycle dynamics is that the probe, I don't have an ER-IR pulse that is 10 femtoseconds. That my ER-IR pulse is 80 femtoseconds. That's it. It has nothing to do with the CP stability of the pump. That's already phase stable.
Attach.
You go back to, again, scattering in the spin sector. So I hear your argument, but I would say that, one way to interpret these measurements is the conditional information you get from the first scattering event. Now, if you have a big lattice, if you have a diffraction limited spot, then the fact that you have generated this excitation is going to have a vanishingly small effect on the next scattering event. So even if I agree in principle there should be some bunching, can you realistically see that?
Well, we actually have an estimate, yeah. No, I mean, for example, in toy model, we can estimate that, yeah, like magnons, for example. I think that produces, well, at least there's no reason why it should be anti-bunched, for example. There's of course some 2-photon components that maybe, there is of course Chi3 type response, right? Which is when system necessarily returns to exactly the same state where it started. So this is like a singular component of the whole scattering. So it's like we have one option to return to the original state and like infinitely many options to go somewhere else. So when we return, this is either Chi3 type response or Chi1, for example, here. But all the others, they are like incoherent noise, basically, bumped due to creation of magnons, for example, or something like this. So I would assume it should be bunched in this case. No.
Any other questions?
Your concern is that how do I distinguish between two different Rayleighs? I have like many sites. Like I detect one photon here and one photon here, or 2 photons from the same spot. I mean, of course, if your system size becomes mesoscopic, that goes down. But there are some of these processes only happen if I have 2 photon processes at the same link or a plaquette. For example, this thing that leads to 2 omega L minus U, if I condition on detecting those photons, then they are certainly coming from the same site. Imagine I post-select only to detect 2 photons. There is no way that the Rayleigh gives me 2 omega L minus U and U.
Yeah. So that should be bunched. I agree. I mean, that's why I specifically asked about the spin sector.
I see. Yeah. So the spin sector would be this guy, that one of its legs should go up to the spin sector for a 0 amount of time and come back. But okay, let's maybe continue that offline.
Okay, so I think we can wrap up the session, and let's thank Andrey once again for the interesting talk.